supply at constant volume. Cp is greater than Cv. By how much? By a quantity equal to Nr, where N is the number of moles of the gas. Therefore, what is Cp minus Cv equal to? Cp minus Cv will be equal to Nr. The difference between heat capacity at constant pressure and heat capacity at constant volume is Nr. Remember that. Cp minus Cv equal to Nr. Okay. This question I must have asked you by now at least a half a dozen times. What is the internal energy U of N moles of a gas? Even I asked you this about 10 minutes ago. What is the internal energy U of N moles of a gas? Well, internal energy U equal to 3 over 2 nRT. Okay. Now, take the derivative of U with respect to T. If you take the derivative of U with respect to T, you get du over dt on the left side. Can you tell me what is du over dt? What is du over dt? Is Cv, the heat capacity at constant volume, and that's why we are doing this. Alright, we get du over dt is 3 over 2 nr is a constant, and the derivative of t with respect to t is 1. So du by dt equal to 3 over 2 nr. Now this is a very important relation. Why? Because du by dt is the heat capacity at constant volume. And what does it tell you? The heat capacity of a gas at constant volume is 3 over 2 nr. Alright, so Cv equal to 3 over 2 nr. Now, I want you to be using your caution here. And the caution is, where did we get this relation? The internal energy of N moles of a gas is 3 over 2 nRT. Now, is it obtained from any established laws? No. We obtained this from kinetic theory of gases based on our assumptions. We used 4 assumptions and we arrived at this conclusion. We arrived at this conclusion based on those 4 assumptions. Therefore, we don't know whether this is a true statement or not. But this is an opportunity for us to test, because heat capacity of a gas at constant volume and constant pressure can be measured in the lab very accurately. So, I can now take N moles of a gas and measure its heat capacity at constant volume and see if it will give me 3 over 2 nr. If it gives me 3 over 2 nr as the experimental value, then I can say, yes, the assumptions we made were right. On the other hand, if the measured value does not give you 3 over 2 nr, then we can say we made a mistake. Our assumptions were not right. See, look at the way science operates. Alright, let's go and have a look at this. So, Cp, we got Cv equal to 3 over 2 nr, and you remember in the last slide we had this relation, Cp equal to Cv plus nr. And if I now replace this Cv by 3 over 2 nr, I can now get Cp equal to 3 over 2 nr plus nr. And what is that equal to? That will be 5 over 2 nr. That means if Cv equal to 3 over 2 nr, then Cp must be equal to 5 over 2 Nr, because the difference between Cp and Cv is simply an Nr. So if Cv equal to 3 over 2 Nr, then Cp must be equal to 5 over 2 Nr. Now the question is, are these relations right? Now how do we know? Well, we can actually go and look at measured values of heat capacities. Do we have measured values? Well, we have, but before we go to that, let me introduce you to this concept. What is molar heat capacity? Well, heat capacity is a measure of the amount of heat needed to raise the temperature of the whole amount of gas. And the amount of gas consists of n moles of the gas. So, Cv is the heat capacity of n moles of a gas. Cp is the heat capacity at constant pressure of n moles of a gas. What is molar heat capacity? Molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of a given gas at constant volume. They increase the temperature by 1 Kelvin, and that will be the molar heat capacity at constant volume. So once again, molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of a gas by 1 Kelvin. And if the gas is kept at constant volume, it will then be the molar heat capacity at constant volume. And if the gas is kept at constant pressure, it will be the molar heat capacity at constant pressure. Now tell me, if you look at this relation, you will be able to answer my question. What does Cv stands for? Cv stands for the amount of heat needed to raise the temperature of n moles of a gas at constant volume by 1 Kelvin. And therefore, what will be the molar heat capacity at constant volume? But all we need to do is divide that quantity by n. Is that right? Because this is the amount of heat needed for n moles of a gas. Molar heat capacity is the amount of heat per mole. So divide by n, you will get the molar heat capacity at constant volume is 3 over 2R. Alright, let's write these things down. Now, molar heat capacity is measured in joules per mole per Kelvin. You see, once you know the unit, you know the definition. You can see, molar heat capacity is the amount of heat in joules needed to raise the temperature of 1 mole of a gas by 1 Kelvin. Joules per mole per Kelvin. Now, CMP, now we're going to represent the heat capacity, the molar heat capacity at constant pressure, we will represent by CMP. And the molar heat capacity at constant volume, we will represent by CMV. So, let's see what CMP is. I want you to look at this again and think about it. Cp is the amount of heat needed to raise the temperature of n moles of a gas at constant pressure by 1 Kelvin. Therefore, the amount of heat needed to raise the temperature of 1 mole, you divide by n. In other words, Cp divided by n is CMP. CMP equal to Cp divided by n, and Cp equal to 5 over 2 Nr. So what do you get if you divide 5 over 2 Nr by n? You get 5 over 2R. And look at this, the molar the molar heat capacity for at constant pressure of any gas is 5 over 2R. Now what is the significance of it? R is the universal gas constant. It means the molar heat capacity at constant pressure for any gas should give you the same value, 5 over 2R. In the same way, CMV, what does CMV stands for? Molar heat capacity at constant volume, will be equal to CV divided by N, the amount of heat per mole. And if you divide this quantity by N, you get 3 over 2R. So, molar heat capacity at constant pressure is 5 over 2R, and molar heat capacity at constant volume is 3 over 2R. That means the difference between CMP minus CMV is 5 over 2R minus 3 over 2R, which is an R. The difference between molar heat capacity at constant pressure and molar heat capacity at constant volume must be equal to R. Now the question is this true? Are we going to get that right? CMP minus CMV must be equal to R. Now this means that molar heat capacities have constant values for all gases. There is no difference between the values of CMP and CMV for any gas. They all will have the same value. And what will be that value? CMP, the heat capacity, molar heat capacity at constant pressure is 5 over 2R, which is 2.5R. That will be 2.5 times 8.314. That will be 20.79 joules per mole per Kelvin. This is the value of CMP. Now, this is the theoretical value. What is the meaning of that? Well, assuming that our assumption is right. All these are based on our assumptions. You see, these results are based on the assumptions we made in kinetic theory. So if our assumptions are right, then the value of CMP for all gases must have a value 20.79, and the value of CMV for all gases must be 3 over 2R, which is 1.5R or 12.47 joules per mole Kelvin. Well, one consolation is we can check it very easily because these quantities can be measured experimentally. Now look at this. Measured values of CMP and CMV shows that for monoatomic gas, this prediction is true, while it fails for diatomic and polyatomic gases. So, are we all right, or do we have a problem? Well, we have a problem. What is the problem? Experiment, I'm going to give you a table of values. So, remember these values. We would expect that the molar heat capacity at constant pressure for all gas to be 20.79, in the neighborhood of that, and the molar heat capacity for all at constant volume for all gases to be in the neighborhood of 12.47. Now look at the measured values. If you notice that heat capacity at constant pressure